This is Official Nerd Business. Hello nerd boys and girls, welcome back to our programming series. Today we will be taking a crack at Euler problem number 25 using Python 3. So let's have a look at Euler problem 25. As you may see on the screen, I have already created the base template file as I always do for these challenges, with at the top copied in the title and description of the Euler problem, and down at the bottom a method for running this on its own, a method for running this within the bigger program, and the actual methods we are going to use to solve this particular problem. Let's have a look at the problem. The 1000-digit Fibonacci number. The Fibonacci sequence is defined by the recurrence relation where fn is fn minus 1 plus fn minus 2, starting at fn is 1 and f2 also 1. This leads to the following list where f1 is 1, f2 is 1, f3 is the sum of f3 minus 1 and f3 minus 2. 1 and 1 together is 2, f4 is 3, 5, 8, and so you keep counting on the last two terms to get the next term. The 12th term, f12, shown here 144, is the first term to contain 3 digits. What is the index of the first term in the Fibonacci sequence to contain 1000 digits? This is a particularly simple problem, in all honesty. We can have this solved in no time whatsoever. And for this we will need to keep track of both the A and B values of the Fibonacci sequence and a given iterator. And if we were to start these out at 1, 1 and 2 for instance, then we can set up a loop. Note also that we are taking in n here, and n is defined as the length of the Fibonacci number. So it's set to the 1000 from the puzzle, but we are calling it here on a length of 3 to find the first 3-digit number, namely index 12. So we're going to test this when we run this on its own, and we're going to fill in 1000 when running this from the main py to also time it. So let's see. While b is the length of the string representation of b is less than whatever number we got, we want to keep on doing this. And finally we want to return I, and for testing purposes let's also print the final Fibonacci number that we calculate. This should give us 10 over 12 when we run this on its own. And it does. And as we can see, the last Fibonacci number calculated was 144. So how does this work? Particularly we use the ability of Python to assign multiple variables in one statement. So here we declare an A, a B and an I, and we set these up to be 1, 1 and 2 as the start of the Fibonacci sequence is. So when we start this function we are equal to already equal to the second index in the Fibonacci sequence, and we start calculating the third using practically the same syntax, where A is set to B, so we take this term and turn it into this term, where B is A plus B, so we take this term by adding up these two terms which are still in these variables by the previous iteration. Note also that this is evaluated before B gets, or A gets its new value. They are evaluated at the same time, or when the Python compiler or interpreter reaches this statement, it assigns the values A, B, and I currently have to these in place A and B's and calculate the result accordingly. And same goes for I. We simply increment I until the one iteration where the string representation of B has an equal amount or more digits than n specifies. And we break out of this loop, and as we can see, 144 was as expected. We return the index. If we were to run this from main.py, here is main.py, and we can kick it off. We would like to run problem 25 with the default argument of 1000. Thank you very much. It took us 300ths of a second, and we got this beautiful number. If you enter this over at Project Euler, you will get the green check. This is a particularly easy problem, so to spice things up, I want to show a structure that we will very probably use in the near future for other problems. In this case it might be a little bit nonsensical, but I do believe the Fibonacci series makes a good subject for practice. So I'm going to define a function. Basically what we're going to do, I'm going to make a function that calculates Fibonacci, and it takes two arguments, namely the starting arguments. There are some Fibonacci-like sequences where you don't start at 1, 1, or where you'd like to start at 0, 1, or Lucas numbers, for instance, are a series that looks very much like the Fibonacci numbers that have different starting indices. So I'm going to make these variables. And then I will also do something slightly differently. I'm going to set up a permanent loop here. This evaluates, I could also be more explicit and always say while true. This will also always be true, so it will always continue looping, but I am not going to get us trapped in an infinite loop here. I am going to do the same thing again, where A and B are set to B and A plus B. Mind that I am not currently using the iterator, it will return shortly. And then I am going to yield B. Now yield is a sort of return statement, but basically what this does is it allows us to it keeps this function open, where usually you would, if you would have a function and this function would define its own variable of some type, you'd call the function, you'd get the return value, and later on you would call the function again. Then all of the arguments you passed previously are forgotten, you are calling a completely new and blank instance of that function. This works slightly differently. Yield turns this whole thing into an iterator. And what it this now is an iterator, and what that basically means is that it creates a list of values, and every time yield is called it returns the next value. It keeps track of everything it does in the function, it keeps track of all the variables, it keeps state, if it were, until you call this function again, or call the next function over this function, and then it yields the next result, etc, etc. So basically you are intertwining control of what this function is doing while keeping this function with all of its variables intact. You are intertwining that, interleaving that with the syntax around the function calling this. So if we were to use this, I could I will leave attempt number 1 as is, and I will create a second attempt at solving this, also taking in an n. In fact, another example of this is this. So when would you use this kind of intertwining? I'm not going to put in any variables because these are already initialized. I will show what happens when you change the variables in a second. This doesn't actually return anything yet. So let's put in the print statement because it will start returning things shortly. And throw in n at 100, 1000, why not 1000, as is required. Alright, so this will this also is an iterator. Basically what the for loop does is it creates the range of from 0 to up to 9, not including 10. And every time the for loop loops over it, it will take the next number out of that range. And what this doesn't do is that it creates a list of all the elements that we were going to get out of this and store it in memory. What this does do is every time it gets called, it creates the next member of its list, and it knows nothing about what's going to follow. It knows nothing if this were the third iteration. It knows nothing about what came previously. It only keeps track of this one value. So a little later on, when we are working with values that are pretty large to store in memory, or a large list, if the list itself in its entirety were too big to store in memory, or if the entire list would take too long to generate and we are only interested in elements piecemeal, then this generator construction, this is called a generator in Python, is exactly what's going to solve our problems here. If for Fibonacci we weren't generating a complete list anyways, we are already looking at the items piece by piece. But the function itself, the structure of keeping track of your variables, kind of shows the point of this function. So this should print out the first 10 Fibonacci numbers. If we were to run this. Great. Except that it doesn't. I am getting an object reference here instead of... Alright, I see why I'm getting an object reference here. I first need to actually instantiate the iterator. If I were to create a variable like this, and actually instantiate my my generator here, and then I can call next on the generator instead of the generator definition. There we are. So if I run this, then yes, we do get the first couple of Fibonacci numbers, but it starts out at index number 2, so we're not seeing indexes 1 and 0 in this case. Well, we can do something about that. We can alter this slightly, and we can say that we want to note that the yield statement doesn't necessarily need to be in any type of loop. It kind of works as a return statement, except that whatever is in your function keeps on being executed. Not in a multi-threaded fashion, by the way. It's not like if we were to have a time-consuming calculation in here that we would yield, then this program would run, and at the same time in the background the next value would be calculated. But it does help when you have a list of certain items that take time to calculate, that you don't have to wait for the entire list to be completed. And I think we will be using that particular trick sometime in the future. So here we first return the A value giving us index 0 of our Fibonacci sequence, and the B value. Well, let's rerun this, and here we are. We get A, which is 1, we get B, which is 1, and you could say this, for instance. And now the first 10 items, of which 8 are generated in the loop, and the first 2 are simply yielded by these two statements. And we can kick this entire series off with completely different numbers, this would give a pretty weird range, I think. So here we are, 2 and 6. 2 and 6 are 8, 6 and 8 are 14, 8 and 14 make 22, 36, 58, etc. So the function works as expected with their optional elements, optional parameters, and the iteration works fine. So let's turn this into the actual loop that we want. For I f in enumerate semicolon or colon if I greater than 10, then break. So we instantiate our generator, then we loop over it using enumerate, and what enumerate does is simply it takes the next element from this list, or iterator in this case. It isn't a fully instantiated list, but it's an iterator. Enumerate works on iterators, and it will return not only the value of that enumerator but also the index. And here we are printing the indices and the values, and if you have 10 items we break. We are going to change this condition a little later on. I'll probably quit printing, but here we are again. And if I is larger than 10, so we take 12 elements including 0 and including the 1 over 10, giving us 144 again. And note that this was 12 previously, so we will probably want to add 1 to a return value when the time comes. Or we want to instantiate this to be 0 and 1, and here we are. We have solved our 1 indexing problem by instantiating the Fibonacci generator with different numbers. But we don't want to break on the 12th element, we want to break on the fact that this happens, and then we want to in fact we don't even need to break out of the loop, we can simply use the return statement from within here. We want to return the index. Now running this, overshoots the mark a little bit. It's not larger than n, larger than or equal to. There we are. And changing this to return attempt number 2. And running main by $25 default parameter. It's equally fast. So this, because this also works piecemeal, this might not have been the best example to introduce this, but since the problem itself was pretty simple, especially for Python, which handles 1000-digit numbers pretty smoothly, I thought this was a nice one to introduce generators. And we will be seeing generators in the future. There are plenty of problems coming up using large lists of primes and some properties of primes, some concatenations of primes, and those type of things. This will be a very handy and very time efficient way of looking at elements on those lists. So I hope you've enjoyed this one, and I will see you back for number 26. Don't forget to check out my GitHub, where you can find all of the source code for these solutions. Link in the description. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.